And your man do I.
Engineer, are you talking to us?
So a part of body. So yes, Doc.
Yes.
So um, let me introduce myself first, Doc. I'm not from this background, but I admire the course, and I've also found myself in that environment. The reason why I'm pursuing this program. So
Okay.
rock mechanics basically has to do with the dynamics of rocks, the structure and the layout of how rocks behaves and their formations.
Okay.
I don't know if I'm on the right track.
Yeah, that is fine, the formation, but we are not so much into the formation of the rock. It is more about how the rock behaves and how it will respond to our designs. Okay, so when we are going more into how it was formed, you are diverting to geology.
Oh, okay.
Mhm.
I am educated, Doc. Thank you.
So, who else?
Good evening.
Yeah, evening.
You just shared what I wanted to see, like how the rocks behave when you apply some forces to them, and whether those forces are from the natural processes or maybe the human activity, how it's going to affect the rocks. That's what I wanted to contribute to the rock.
Beautiful. This man is talking like someone I have taught. Let's move on. Okay, Khaled.
Okay, I think the engineer who just spoke also spoke what I wanted to say. I think uh, rock mechanics is how the rock matter responds to stresses and disturbances created by so
Okay,
that's the little thing I wanted to say. Thank you.
beautiful. Mohammed Tiari,
Hello, the subject concern the response of rocks to enable disturbance.
beautiful. Who else has something more to share? Who else has something more to share with us? Is Mohammed's hand still up to add more? Okay, so it is that aspect, okay? When you go into the mining industry, you realize that just see the mine as it is, that company you work in, as some kind of a country on its own that has got several departments, several ministries, okay, and sectors. And every sector at the end of the day come together to make sure we have a consistent governance, okay? That will make sure we do not go in there. You go in with 10 fingers, you close from work in your reflective vest with your fingers intact, 10. And so whose duty is it then to be sure or to ensure that when you enter the pit or you go underground, that fellow has been able to check and is very much aware that this space that Kwajo is entering is in good condition. And then even before the mine planner or whoever decides that we need to create a space this big, he will take consultation from the rock mechanics person who in the mines you address as the geotech officer. So that person's duty is to always ensure the integrity of our designs. Okay, so in simple terms, studying rock mechanics will help you to influence designs that come up from the technical team in terms of the mine planning sector or the drilling and blasting unit when they are coming with their blast design, they will pick information from whatever data the geotechnical officer has got. Oh, this side of our wall, we have a problem with it. And so please, when you are drilling, do not do this. Do not charge this place at this with this quantity of explosives. Else, by the time we wake up the next morning, that side of the wall is down. And so to ensure the integrity and safety of our designs in the mining company, the body or that particular entity in the mining company responsible for this is the rock mechanics person. And that is why I state that you are not so much interested in how the rock was formed. Of course, if you get to know the basis of them and their names and whatnot, you are doing geology. And that's why I always say geology, they are there to do those studies and tell us how the rock was formed as if they were there. And then give us beautiful names like Grewa Case, Akos, and conglomerate, granite, and hair. They do naming ceremony for rocks. That's what they do. We are not like that. Mining, we are interested in what will happen to this rock if an excavator with this load passes over this particular rock material. What will happen to it? Will it be able to contain that load? If it cannot, then what can we do to augment the safety of that rock or improve upon its strength to be able to handle that amount of load? That is rock mechanics. I see a hand coming back and forth. Hello. Okay, maybe your question is answered along the line. So let's move on. So that is why we are supposed to study rock mechanics. Again, we want to throw a blast. When we throw that blast, there is that tendency of that disturbance within the space we are working, which can transcend into our walls. And at that point in time, you ask yourself, what if we fail with our estimation and it gets into the wall? What will happen? Again, the rock mechanics person is supposed to have given you information on that rock you are dealing with in mine A or B or C to tell you this is how hard, this is how soft our rock material is. And so at this point in time, no, don't try this amount of explosives or don't drill this big in terms of your diameters, okay, of your drill holes or whatever, to ensure that you do the right thing. Yeah, Mahama, carry on.
Doc, please, do they do an initial study in the beginning to determine what the area looks like? Or as and when they are about to drill, they consult the rocks mechanics person?
Okay, so the general practice is that before drilling, we learned from our introductory class that there's something called exploration. So before we go into the actual production in the mines, we had already done that exploration activity and we got some scanty data, which we are using. We'll go into detail with that, which we are using to have more or less a fair idea of how our rock is in terms of competence. Because remember, in that class, I mentioned that you can decide a particular mining method based on certain criteria, rock strength, country rock strength, and then ore strength, and those properties. You will use that to decide what mining method. That means you would have done some study on that exploration data you got, giving you a fair idea of the competency of the rock, that is the ore and the country, which is giving you that idea that you should go with underground or surface. And when it is surface, go with this bedding and spacing or hole diameter of this and this type of explosives that will give us better fragmentation. So all of that are done. And as you go along, the property of the rock might change. Then again, we go to drill and get core samples whilst production is ongoing. bring them to the lab for us to conduct tests on them, give you the necessary reports in terms of the new data regarding that particular rock samples you brought, and that will update the information you got earlier when they were doing the exploration processes. And that is how we go about this whole thing. So
Thank you.
it means rock mechanics is just like the thumb. You go into the pit, you come out smiling and doing go ahead, go ahead. It is the geotech officer. Once he relents on his duty, you can't say go ahead again. And so it is something we need to take very serious if you are interested in going into the geotech side to appreciate how the mine manager is in your hands. Then you have to study this course and get a very good knowledge, an in-depth knowledge about rock mechanics. And I bet you it's an interesting area that every mining engineer must get to appreciate. And that will let you more or less appreciate designs when you get to the mine. How come you go underground? Sometimes there are no bolts, no netting, nothing. And you are able to go in there and come out. Have you ever wondered? I taught a foreign class some time ago and I asked them about underground mining as what? The response. So we want to see if I punch this bottle, what will happen to it? If I am interested in studying what is going to happen to a piece of rock, then I am doing what we term as what? Rock mechanics. Then the disturbance which we induce onto this rock material, it can be caused by man or be natural. So rock mechanics is more or less a theoretical concept, okay, an applied science of the mechanic behavior of rock. So here I am interested in looking at I am looking at the theoretical concept, which means we are going to be dealing with certain mathematics here and there. And then now see how these theories we are talking about can be applied. Okay, so if we apply the theories, then we are looking at applied rock mechanics. So I study the rock, check to see what is happening after the punch. If I study those mechanisms and I now want to apply them in my field to do any designing, then I am looking at applied rock mechanics. Then it is that branch of mechanics concerned with the response. So again, it is an applied science. When I say rock mechanics, it's a theory or a discipline on its own. It's a field. So it varies. And everyone, when you go to the petroleum, they also study that. And they will, as we go deeper, I will show you the aspect of the rock mechanics that the petroleum engineer will be much interested in when he's studying rock types. So it is the branch of the mechanics concerned with the response of the rock, okay, to force fields of its physical environment. So as the rock is found in there, you just want to find out what is happening around this particular rock material. If I'm interested in things like that, again, I am looking at rock mechanics. So what are some of the basic concepts in rock? And with this, there are certain basics or certain properties of the rock that are similar to soil. And so in this class, to enhance better understanding, I will merge a bit of the concept of soil so that we appreciate some of the formulas and principles that we are going to be dealing with in our calculations. Okay, so rocks are aggregates of crystals and amorphous particles that are being joined by varying amounts of cementing materials. So it means if I pick any piece of rock material, it is not like that rock material just came to be, but rather it is as a result of tiny particles that looks like soil, okay, the particles of soil that have been put together as a result of certain mechanism. It could be certain forces due to pressure, okay, that have brought them together, these tiny aggregates together. And sometimes when they come together, they could give certain definite shapes. And when they are like that, the geologists call that crystals. And then they can also come together and give you some irregular shapes that you cannot even define, whether it's rectangle or whatever. You find it difficult to say. And so when it's like that, we say it's amorphous. And then rock is made up of minerals of more or less invariable composition bounded together by forces of what? Intermolecular interaction. Okay, so if I have any material, the particles I talked about, it is these particles that have come together in varying form. It means it's just, let's just consider the formation of the rock to look more like you are buying gobe, okay? I think everyone here enjoys that. So the foreign student, do you know what gobe is?
Yes, dog.
Yes, dog. Yes, dog.
No, please.
Yeah, nice
Yes,
one.
dog. Yes,
No.
dog.
No,
Yes,
no, no, please don't.
yes,
That's
dog.
Okay,
Gary.
No,
Gary.
you
good.
know, go there. Go there.
Gobe, nice one. So let's just imagine the formation of the rock being you putting Gary and that of what? The beans, bringing them together. And then at the end of the day, you getting it to mold. If it is to mold, something will help it to do that molding. It means the water is also playing a role. Your oil at the end of the day can even be there and sometimes make it difficult for you to bond them. The oil will try to split them apart. So it is these varying components that are coming together by way of certain molecular forces that are inherent within the various particles, bonding them just like magnetism, putting them together. Or there are certain particles that will bring them together. So it's either the inherent forces that exist within these rock particles or the tiny particles that attract each other. And at the end of the day, when they are there over time, they stack and become a piece of rock. Or I have the type where a piece of rock and another piece of rock, and maybe as a result of certain movement of material, they bring these particles together and attach them. And over time and certain activities, they get stuck together and you have something you call rock. And depending on how compacted they could be when they are formed, we have the various types of rock, which we shall talk about. So soil is the unconsolidated mineral or organic material on the earth, okay, on the surface of the earth that has been subjected to various environmental factors. So if I then have this piece of rock and then we scatter these particles together, they are reduced to their barest minimum, then I am looking at what we call soil. So soil is unconsolidated type of mineral. And then soil is a product of weathering. What is weathering? I have a piece of rock, and with this piece of rock, as it rains and the changes in the weather keeps bringing about something we call expansion and contraction within this rock material. Then as it contracts and expands, there are cracks and other things going on within the material. With time, it loses its strength. And before you know it, it begins to disintegrate or fall off from the parent material. And then at the end of the day, you have soil being formed. Okay, so disintegration and decomposition of the parent rock, either residual at the parent site or transported from. So it can be residual, as in if I have this as the rock and then it begins to disintegrate, they find themselves at the base of the rock. Okay, or this material that are disintegrated from the parent find themselves being moved as a result of wind or water or any other transportation agent to a different field, then we are forming what we call soil. Okay, so these processes are facilitated by erosion, the wind, water ice, and then other gravity. For example, how does gravity come in? Assuming it occurred on a hill. When they pile up and keep piling and keep piling, a time will come they can no longer stay there. They begin to slip off, and that is gravity occurring. Okay, good. So let's move on to the next. So rock, as one of the most commonly used construction material, is very complex and difficult for us to describe and define. It is not like a piece of block where you are the engineer. Perhaps you are a civil engineer, so you designed it yourself. You know how much cement went in there, how much of sand is there, how much of gravel you have in there. You know all of these things. The compositions are known to you. So it's easy. If you test the strength and it's not good for you, you can easily vary your components and you have a different piece of block with different strength behavior. But then, colleagues, with this particular rock that we are dealing with, the natural one, you do not have control. And so it makes it difficult for us to discuss, define, and give it a distinct definition. And that is what this slide is about. So to avoid structural failure that is associated with this rock, it is an absolute necessity, okay, for us to understand the rock, study it, understand it, learn to control it, just how it is. As someone would say, famisa. So you know very well this rock is weak, but you need it to do your designs. You cannot augment the strength, change it, or even remove it from that location where it is to another. So let's take, for example, you have designed your ramp on the left side of your whole road, your pit. Then as you go along, you realize there are difficulties, or even the left side of the pit is closer to your plant. So you are fine putting your ramp there. Then later you realize this rock is exhibiting different behavior. You don't have control over that. If you cannot do cutback to solve that problem and create a new ramp, then you have to move it to a very far end or try to change the entire idea of that design. That is what we mean by understand it and learn to control it within its natural environment, because where it is, you can't move it to another. Then, whilst it is in its natural environment, it has got certain friends that it plays with. And those friends will continue to be there. So you have to deal with the rock there together with the accompanying friends. And those friends are what? The load, which is your dump trucks, your excavators, your drill rigs, your LVs, the human beings, moving back and forth, your water bowsers, using this whole route you have created within this rock material. So the load will be there. How do you deal with the rock? Learn to understand, control it under the influence of the load. Then again, water is there. So the dewatering team will be having sleepless night, trying to get the best pump possible. That can help us manage the water because the water is with it. You can't change that. Then the last thing is temperature. If it is surface mine, you have the scorching sun on the rock. When the sun settles, it contracts, expands. These things are things that can influence the behavior of the rock over time, but you cannot take that away. If it is underground, again, as you go deeper and deeper, the load will increase. You will be hitting water. And then again, the temperature down there will keep increasing. And where your mine is an low mine that cannot provide you with the best refrigeration, and all they can do is give you some hot air, claiming it's oxygen, you go down there and come out and you are all wet. That's the temperature for you.
Okay, scaring some of us.
So Wisdom, you have something?
With your last comment, as he said, providing you with some air, claiming it's an oxygen, you are scaring some of us.
Oh, but that is the truth.
Yeah.
Just look at the air you are enjoying on the surface and go underground and see what is there. I don't know if there's anyone who works underground in our class today that can share
Yes.
with us the difference in the
Sir,
air.
but we have the artificial and the natural one. So this is an artificial made.
It is not supposed to be an artificial. It is fresh. That is pumped from the surface. But because of the various transitions that the air goes through before it gets there, by the time it gets there, it is hot.
Yes, exactly. So it's from the portal into the down. So as the portal suck the air into the mine, then the secondary fans will be pushing them to the headings. So as they are pushing them to the headings, it will be circulating. So the secondary fans there generate in the system of, maybe it's like turning on your fan in your room. You see, the fan is not producing any air, but at the end of the day, circulating the air within the room. So that air pushing and passing through the system, heat can also generate another heat affecting the air, as you're saying. So it is true. Thank you, sir.
So you have the air. So that's why sometimes you can have fan in your room turned on up to 5 or 1, whichever is your highest revolution. And then you still sitting there and be sweating. Because if your doors are closed, you have the fan on and you can suffocate to death. Because the air is not coming from anywhere. It is what you are sitting in that is being circulated to sweet your body. And so you need to provide another avenue. Yeah. Frimpong.
So that is why if you go to UDS Nabrongo campus, they will tell you always put your fan at 1, because if you put it at 5, you'll be suffocated.
But Doc, some of the mines, they do have refrigeration plants that send cool air underground. So it's not entirely the hot air. Some of them you can really enjoy. I mean, most
Exactly.
of the
That's
places
why
I've been.
that is exactly the point I made. I said where your mind has refused to provide you with refrigeration, okay, and rather giving you the one from a low mind, okay. When it brings you that one, sometimes even the machine pumping the air, it's a machine, so it get heated, and so what it is providing you with, it has already heated it and passing it on to you. Okay, so these are the challenges with us when we are dealing with our rock. It's a structural material that has got all of these elements coming together, okay, for you to manage it. So you are managing the rock together with these elements we have made mention of. You don't have control over them. So rock mechanics is a discipline that uses the principles of mechanics. So here, what we are trying to say is when someone comes to do mining engineering, we expect you to have an engineering background. Why? Because mining engineering is not a pure science, but rather an applied science. And so we expect you to have done engineering. And with that engineering, what are some of the things you do there? You do what we call mechanics, and that is pure science. So you study those principles, and when you come to the mining class, we go to a class like the rock mechanics, and then that particular subject will tap knowledge from that applied sciences that you have, the pure sciences that you have done, and then align it with what your problem is. And so we say it is unapplied. So it is going to borrow certain mechanics principles, which is the word mechanics is already a pure science somewhere. You pick it up, study the theories and the concepts there, come to this class, then we build on top by way of applying those principles into our class and our lesson. And that mechanics we are talking about, all they do is talk about metal. But here you are talking about rock. They are not the same. But then the principles are being borrowed. So when we get there, we'll discuss that. So what are some of the differences here? So we have normal construction material, and then they have certain behavior. So normal construction materials could be the steel, the concrete, the mechanics, okay? The mechanical behaviors of these things are continuous, homogeneous, isotropic, and then linearly elastic. And then we give it an acronym called Chile. So in the OBJ, when you see Chile and Chile or Chile, Cheles, please watch. You'll be able to answer. So what does this what does this mean? So a normal construction material, take for example, a louver blade or a tile that you've purchased with your coin. At the end of the day, when you go to the shop to purchase this tile and you see that it is cracked or broken, I don't think you will see it and still pay for. Why? Because it is a normal construction material which we know that it was designed from factory, and so it should be smooth for you to use for your purpose. As soon as there is that crack, it ceases to serve its purpose. So if you are getting it just as it is, it's perhaps the woman says, oh, where's our boy? They mean to me financial. You give me, if the thing is sold 120, you say, oh, you give me 50 Ghana and add it. Then with that one, you will gladly collect, because you at the moment the person tells you, oh, you give me so and collect, you remember that you might be doing some patching in your washroom, so you will need it. But when you have to pay full amount for the broken tiles, it becomes trouble. So we expect that something that is made where man has control over must be continuous. There shouldn't be any crack on it. It must be homogeneous. Homogeneous in the sense that the various particles that came together to give us the rock, which we have mentioned earlier, that it is made up of aggregates. All these aggregates are uniformly mixed. So take it as a piece of block that you have asked a mason or whoever to help you mold. If the person fails to mix the cement well with your aggregates, and then the uniform proportion of the water, what do you think happens? You will see the piece of block, and then there will be a chunk of sand hiding somewhere of the block. As soon as that piece of block dries up, you see that because that section did not get the cement, it begins to disintegrate from that section. So what we are saying is that if something is man-made, which is a normal construction material, we have control. We have control over its formation and how the components are to be mixed. If it is 1:1:1, we know 1:1:1 is what we should use. We ensure we mix everything uniformly. And when we do that, we get something we call homogeneity. Then we have something we call isotropy. Isotropy here is talking about once the substance is uniformly mixed, if I test for its property in terms of strength at any dimension or any part of the material, I should get the same value irrespective of the orientation. And that is isotropy. Then linearly elastic is talking about anything that you exert force on, which is a normal construction material. It is assumed that when I apply the force, that particular body is supposed to respond correspondently, okay, on the other side. So for example, if I press harder on a piece of ball, the amount of force I am using to press will determine the amount of squeeze I will get with that material. If it is a rubber band that I want to stretch, the amount of effort I put in will reflect in how much length I will get. And then when I leave that material, it can go back to its original state. So the elasticity we are talking about here is talking about the correspondence in terms of you applying force and that material also being able to reflect or respond to that force linearly. So at the end of the day, I give you one slab, you give me one tier. You get a second one and I see two. So when I'm to plot graphs or these points at the end of the day and I draw a straight line on it, I should see the line being straight, and that's what we term as linear. Yes. Chris, your hand was up.
No, before I forget my question, please, with the chili, from your definition from the continuity to the linear elastic, meaning it doesn't describe how the rock actually is, but it helps you or to represent the simplified theoretical of the rock in terms of analysis.
Exactly.
So meaning it is unrealistic, right?
Yes, that is exactly the kind of thing we are talking about. But because it is a normal construction material, you have control and you can design to meet these standards. And that's why I use the example of the tile. You don't expect to design a tile for sale in the market, only to finish with the design and see that there are cracks or the back and the front of it are all rough. No, you are wrong. So it's predetermined. When it comes to normal construction material, you have determined the component that should make up that element, and you have a fair idea what your output should be. Let's take, for example, cement production. We are designing cement. So there are certain elements that we need to put together to give us a particular strength of the cement. And so we cannot have the cement being produced giving us less of that strength that we want. The moment we do that, it is wrong. Per our design and our standards, we have made a mistake. So in our next production, we have to correct that. But when you come to the rock, as soon as you go in there and you excavate and you see the rock having cracks inside it, there's no way you can go and put it in there and then have it reformed to have that complete surface you are looking for. You can never have that. So let's look at this. So we are saying properties of the man-made materials are known and controllable. Yes. Sylvia?
Yes, Doc. Doc, what I know about a material being linearly elastic is that it can return to its original shape when stretched. Okay, so my question is that is concrete linearly elastic?
Okay, so
Because that's for steel.
what we are talking about here, we are talking of the
Yes.
linear in the sense of you getting in terms of
A
the
response.
force, the response you this thing you give to it, the response it gives you. At the end of the day, when you plot, you get a linear line. So take for example,
Okay.
if I have this, but the one you are talking about is what we term as elasticity, which is a complete
Okay.
property, a different property of the material we will talk about.
All right. All right. Thank
Are we
you.
fine?
Yes, I'm fine.
Good. So let's then take a look at properties of man-made material. We say they are known and controllable. And I've explained this in the properties, the chili I described, that you know if you are creating an iron rod, you as the manufacturer, you know the various elements that should go into it to give you a particular thickness or strength type of your iron rod. So the properties are known. And so where you mess up, you only get some deduction in your salary, and your next production, you do the right thing without messing up again. So you have control. So it is controllable. But let's go to Almighty Rock. Almighty Rock says that due to the existence of the discontinuities that are there. What are discontinuities? It means that the rock surface may not always be smooth. An excavated surface is always rough with lots of cracks, lines everywhere around that material. If you are getting one that is that smooth, it means you intentionally went into a portion of it and decided to cut it to get a smooth portion for a particular purpose. But rock naturally is made up of, talking about rock mass, generally, you have discontinuities in there. It is inherent in that rock material. The next one, the behaviors are discontinuous. They are inhomogeneous, or in other words, heterogeneous. What does that also mean? Let's use the homogeneous to describe that. Homogeneous, I said, you have all your elements coming together, uniformly mixed, such that when I fetch from any angle, irrespective of my location. So let's use the Gobe principle again, or analogy. With the Gobe analogy, you go to the woman, you tell the woman, oh, I want this amount of Gobe. The fellow should be able to measure the quantity in the number of ladles, and each ladle is assumed to have a certain quantity of beans in there. So if you are using 3 ladles, you get your 3 ladles, and you know the definition or the quantity of beans that are in there. The amount of water in it is the same. Then you have your gari. All of these also in measured quantity. You have the quantity of oil that will mix these things together for you to have the gobe. Such that if I fetch from any angle of the gobe, assuming we are a team eating, the amount of nutrition Kojo is getting from his side of the bowl when he fetches any spoonful should be the same as what I am getting. And when you are measuring that property, is what we term as that particular term isotropy, when I determine the strength property. But then in our case, when you come to the Gobe scenario here, you fetch, this woman is in a hurry to give it to you and serve the next customer. So you come and you realize you have some black water at one corner of the poly bag. The oil has not found its way there. At one section, you have some white gari sitting there. And then your beans, you bought 20 Ghana. Another came and bought 20 Ghana. You realize that your case, you were given 2 and a small piece of ntoswo, 2 ladles with some small, this thing. Another comes with the same 20 Ghana. The fellow is getting 3 ladles full with ntoswo. So you realize that when you put these things together and mix them, hardly would you get the whole thing being uniform, such that you fetch from any location of your bowl and you have the same behavior, the same quantity of oil, the same quantity or number of beans, the same quantity of gari. And then if you even take it to the lab to squeeze the water content in the gari, you won't get the same. So if you are able to get the same things, then you have homogeneity. But where you don't, we say it is heterogeneous. And that is the behavior of our rock. The rock is never the same. Why? Because assuming volcanic activity taking place, which we know when it happens, it gives birth to a type of rock, isn't it? So if there is volcanic eruption where sedimentary rocks are brought together, metamorphic rock is coming from the north, and then you have some hot air blowing somewhere, all of these things coming together to give you that formation. At the end of the day, either it dries in the open or it cools within. So you have intra and extra. So all of these would define the property of the rock. And due to the heat or that nature, no human being can stand and say, hey, we want a homogeneous rock. So all the engineers come around. This volcano that is happening, we need to be there and then stir the mixture so that we get a uniform rock. So that if I fetch any quantity of the rock sample, I should get the amount of mineral content that is in the rock being the same. Nobody does that. So it is a natural phenomenon that occurs in its formation. And so you don't have control. So in that case, when the formation has been done, I don't think if you try to measure their strength behaviors, you should get the same values. They will change because you measured it from the X side. You realize that portion, there was more of a particular mineral component, which has more competence over another portion where that type of mineral was not present. So your rock will never have the same strength behavior in orientation. Then, when that happens, there is no way you can give it certain force for it to respond more or less linearly. So as the Y increases, you have your X also increasing. You can never have that. And so you have some zigzag lines forming, curves that you cannot define. And so when it happens, we say it is non-linear. And in that case, your rock is given this beautiful acronym, which we will call on the ladies to help us with the naming ceremony. Please, how will we call this acronym? Whatever name you decide is what we all go on with.
Portia, go ahead.
Eja Kresi, what's the name?
Portia will help us.
Huh?
Portia, my.
Okay, Portia, are you there? What name are you giving to the acronym for the behavior of rocks or the property of rock?
Diane.
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 I think if we say Diane, it sounds familiar.
Diane.
Yeah,
What is this?
I hear Rebecca said, Diane.
Okay, Diane. What at all
It's
is
there.
this?
It's lady's name. Oh, it's Diane. That's how they spell Diane.
Okay, nice one, Diane. But if you don't
Yeah.
take care, you will swallow the eye and have yourself in trouble. So we say the rock. Yeah.
Diane for short.
Diane. So in this case, we say chili. Diane. Okay, chili or chili. This one is talking about continuity, homogeneity, isotropic, and then linearly elastic. And then we have discontinuity, inhomogeneity, then you have anisotropy, and then non-linearly elastic.
Diane
So
in Chile.
I want to understand something.
Yes.
Practically, meaning with the Diane or the last one, you are going to need the help of, let's say, assuming maybe field mapping and laboratory testing, some labs. But with the first one, you can just be there and estimate. Is that the difference? I just want to understand if that's
Yes,
how
the
it is.
other ones you can always just watch them, but the anisotropy you
Okay.
can, yes, of course, you getting knowledge in this behavior of the rock. There's no way you can make that assumption that a piece of rock has the same strength when you measure it at the north side. You should be expecting the same behavior of the rock when you go to the southern part of your mind. No, that is what this anisotropy is trying to tell you.
Okay.
Or when you see rock material at the surface of, let's say, level so and so, you go to level 110, you don't expect to see the same behavior of that rock, the properties you exhibited at the top. You shouldn't expect the same at the bottom. So this one too perhaps will need some lab work to determine whether they are the same or not. And then you have the elasticity here also giving you lab result. Is lab result that you can use to determine that. But the rest of the things are just from theory, where you can just know that these are the common behavior of all rock masks. Are we fine?
It's left with the first one, the chili.
Yes, so the chili too, we are saying they are continuous because the output that you get is predetermined.
Okay.
It's
It is an
predetermined.
assume.
Aha. So you know that if I am making a book, I don't expect that at the end of the day when I've created a book, it should come out with perforation in it. Who will buy? So they are predetermined. And where you make a mistake, you have that control because you are the one that put the elements together to give you that.
Okay, I'm okay. Thank you.
Good. So that is it for this slide. And I think we have to end here. So look at the engineers there in the space, that excavated space. They are trying to measure discontinuities and other things within the rock material using line mapping approach. Okay, they want to check the discontinuities you see, the cracks that are all over the rock material and at what distances these are happening. So this is what you see in the mine every day. And you have to make decisions based on this thing you have seen. You don't have control over how the rock was formed. You go to the northern side of the mine, you pick data, you come to the south, it is a different story. You go to the eastern side, you cannot use the judgment you made at the south and the north. You can't come and use the same story there at the eastern side. And that is the gospel according to rock mechanics. So I would like us to end here, and God willing, tomorrow when we meet, we can continue. If you have any question, you bring it up. Otherwise, we close.
Doc, please, can you please share some small light on the elastic for me? It's like I'm not really getting that one.
Elastic. So elastic here, we are talking about the proportion in terms of how much deformation the rock is able to make when you apply certain forces. And of course, some of these forces are such that when you are talking about elasticity, the one your mind is on is more about elasticity. It is the property of the rock that states that If I apply force on a particular load on a particular material, so long as that material has not exceeded its threshold, when I relieve the load, it should come back to normal. That is elasticity. But then this one, we are referring to that behavior of the rock that helps us to measure at a time. When I apply the first load, assuming I want Engineer Cressy to carry 10 bags of cement on his head. If I place the first bag of cement and I'm able to quantify the amount of stress on his neck, I put that down. Do the same for the weight of the cement. I put the next bag. I measure the deformation that is happening. Is it corresponding? In terms of when this increase, does this also increase or does it decrease? If I am doing that and I finish and plot a line, I am going to have a straight line. And this is what we will say the material is linearly elastic. It means the amount of force correlates with the amount of deformation.
Can also make a contribution.
Are we fine?
Yes, Doc. Thank you.
Okay. Someone else also wanted to talk. Okay. Any other?
So, Doc,
Hello, Doc.
it means looking at using the rock for your explanation means under low stress on a rock, meaning it's going to behave linear elastic. So as it approaches failure, meaning when the stress becomes too much, then it's moved from the linear elastic to inelastic.
And this one, you have jumped straight away from this class to our later slides, where we will see elasticity, looking at how various rocks will behave when you begin to apply load. The moment the load begins to go up, take for example, sedimentary rock. If I pick a sedimentary rock, what do you think will happen? It has got certain empty spaces all over it, isn't it?
Yes.
So when you place load on it, immediately, instead of going up, it will shrink as if it has failed. What do you think has happened? All the empty spaces in it has escaped. The air voids and empty spaces are all gone now. Then that rock material becomes very compacted. Then it will begin to exhibit odeshi. So whilst you add more load, it keeps progressing. It gets to a point, then it changes the behavior again. And so you will draw the line and it gives you certain curves and whatnot. So it will fail at the beginning, then begins to respond nicely. Then getting to a certain point, it fails again. And that is sedimentary rock. So if I pick another rock, which is, let's say, a granite, it will also behave differently. But where I create an iron rod, and I am responsible for the various components and the diameter sizes and whatnot, if I cut them into pieces and I pick every one of them, I'm expecting that when I add each load, I keep pounding on them, it should exhibit certain behavior all throughout to the end. I plot my graph, I get a way to measure the formation and that of the force applied. Then I can say, oh, this is how it is behaving. But the moment you do it and you have failures and certain misbehavior along the line, it tells you something did not go on well with your construction process. And of course, with our rock, each time it fails. So when we get to those sites or that particular section of our studies, you will get to know that our rock is a deformable material, just like other construction material. So when we are subjecting it under stress, there are certain things we measure using machines because, of course, if you want to measure how your rock is deforming, to see how much load it can take before it deforms, there's no way you can let it deform first for you to now put it together to measure how much it deformed. So we have to do this concurrently using a machine. Are we fine?
God bless you, sir.
Okay. I am usually interested in first impression. Mosha class never say. Omo to me who that you know.
And you better cry.
Mame Portia, what will be album? We be say or say
Yes, yeah, boy.
yes, we see boy exactly. Okay, someone says it will go well. So it's an interesting area of our engineering field, mining specifically, which we cannot joke with. So let us try and then appreciate it, and we will enjoy. Okay, so if we don't have any further question, kindly, class rep, inform the class that I am expecting 142 as of yesterday. Was it this morning when I checked? I'm expecting 142 people in the class. So if you do not come and I begin to take attendance and you miss out in a couple of them, I won't allow you to write my test. You have to come and register for this course again. So please inform your members that attendance is compulsory. Now it is 148.
Dog, they beg.
Oh no.
Dog, abotre.
No, we need to understand that